conduction in steady state in 1D. So this is now week 5 of class. Let's recap what we have seen so far. Week 1, energy balances, in which all we did was heat in minus heat out plus heat generated equals heat stored. That is essentially a bank balance of heat. In that class, we also saw that heat is enthalpy. And because of that, we delved a little bit deeper into the concept of heat stored in the form of enthalpy, and that accounts for phase changes or not. If there is no phase change, the relationship between temperature, between enthalpy and temperature, the derivative of that is specific heat. We also saw that if there is motion of matter, as the matter moves, it brings thermal energy with it. Some of these, when in an open system, mass comes in with thermal energy, or my mass might go out and takes away thermal energy. And this way, we can account now for systems that are open, such as a heat exchanger. And this concept of advection is a concept that is not dealt properly in any book. And I wanted to make it clear such that we can make understand many of the things, the systems we're looking for. On week 2, we said, okay, this heat in or heat out has some mechanisms. And the mechanisms can be convection, can be radiation, or can be contact. All three of those over the surface of a body, the outer surface. In addition, we talked about conduction, that is a heat transfer mechanism that goes inside. That was week 2. In week 3, we said, okay, let's assume that we have no gradients inside the body. If we have no gradients, conduction heat transfer is 0. And then whatever is inside the control volume that doesn't have gradients can be considered captured with a single value of temperature T. And that analysis, in which this temperature T depends on time, this is the lumped capacitance analysis. And when we write the equations in this case, we end up with a first order ordinary differential equation that depends only on time. And we did this equation for heating, for cooling. We did it for phase change, like the case of freezing of water droplets to make snow. We did it for the case in which there is heat generation, such as the case of a semiconductor chip that is running at a temperature and the fan breaks down, and then the chip might melt down. Those were the first 4 weeks. And the first 3 weeks. In week 4, we said, okay, if in week 4, we said, okay, in lumped capacitance, we assume there is no gradients in space, no thermal gradients. What happens if there are gradients? And we said, okay, if there are gradients, we have to make our control volume very small in the direction of the gradient, such that we can make kind of a lumped capacitance consideration for each differential control volume. And when we do that, then we end up with an equation that depends not only on time, like lumped capacitance, but now depends in space. And we did many derivations for 1D. We consider heat losses in a bar, heat losses in a tube. Then we made considerations for heat losses in something that has both motion and conduction. And we saw that the Peclet number tells us in the 1D case who dominates in the direction of fluid motion. If Peclet number is large, means the fluid transfers most of the heat by advection. If the Peclet number is small, most of the heat is transferred by conduction. And then we generalized all that. That is what we just did today. But we didn't solve any problem in particular. We were setting the stage for different types of problems. Something else we saw is that if we make a differential control volume just on the surface, we can relate the heat losses on the surface to the conduction of heat under the surface. And in this way, we can relate the gradients inside the body to the temperature jump between the surface and the external fluid or surrounding temperatures. And when the gradients inside the body are much smaller than the jump in temperature, then is the case of lumped capacitance. And this ratio, we called it the Biot number. So now we know two dimensionless groups that are very important for us in heat transfer. One is this Biot number that tells us if we're going to have gradients or not inside the body. Okay, to be clear, you always have gradients if the gradients matter or not. And if the Biot number is very small, whatever very small is, that everybody might have different understandings, but we all agree that if it is very small, eventually the gradients don't matter. If it is not small, the gradients matter and we have a problem. And if it is really large, we can play some tricks like saying, okay, the surface of this body is quenched so intensely that we might as well say that is the surface is at the temperature of the fluid. The other dimensionless group we saw is the Peclet number that relates advection to conduction. Now in week 5 of classes, I want to do something similar to what we did in lumped capacitance. In lumped capacitance, we said, how about no gradients? Let's look at temperature evolution. Then we looked at all these differential control volumes that I put them all together. And I'm going to say in week 5, let's look at something that has gradients, but doesn't matter, doesn't vary in time. It's like the exact opposite of lumped capacitance. Lumped capacitance, let's see how things change with time, but there is no variations in space. Today and until Friday, we're going to say, oh, things change in space, but don't change in time. Steady state. I'm going to start with the simplest case, 1D. And what we're going to see is that in the 1D case, there is a proportionality between temperature difference and amount of heat transferred. And this proportionality is analogous to to that in electricity, in which you have voltage and current. And for that reason, we're going to create the concept of thermal resistance that makes intuitive sense, but we're going to give it a formal meaning with which we can make very complex calculations in a very easy way. I'm going to explain this properly now. So let's see. Let me share. Okay. So here are our notes. Let me these things set up. Well, what's going on in here? All right, we're good. So let's look at conduction in steady state. I just mentioned to you that we are going to see a proportionality between the absolute value of heat and the absolute value of temperature difference. In this case, I put the absolute value, so we don't need to worry about signs. But whatever sign convention you have, whatever it is, you know this, that heat goes from hot to cold. So that's what really matters. And similarly, in electricity, people know that current flows from high voltage to low voltage. So whatever the sign convention is, we know this is proportional. And when we define resistance, it's always going to be positive, same as in electricity. Okay. How do we get into this business of 1D, of steady state heat conduction? And let's start in 1D. The easiest is the plane wall. When we talked about issues of geometry in heat transfer mechanisms, we talked about how the heat flows and whether it's 1D or 2D or 3D. Keep this in mind. Most people, when they see a wall, they think it's a 2D thing, right? If I have this sheet of paper here, you would say, oh, all right. If you have a sheet of paper, the sheet of paper is 2D. However, heat transfer across that sheet of paper is 1D. And why is it 1D? Because assuming that across each side of the sheet we have the same temperature, heat is not going to move up or down or left or right. It's just going to move across. Anywhere on the page, heat moves in the same direction. Right? It doesn't move sideways inside the wall. So in the plane wall, we are going to look at the temperature distribution. So here we have a plane wall. I'm going to put a coordinate, the x-axis against one wall. Let's call this wall 1. And the thickness of the wall, I'm going to call L. This is what the book uses. And I don't know, it makes sense to some extent, but we typically say L is a length, and in this case, the wall, this is the thickness. The reason is we use L is because it's the distance that is traversed by the heat as it moves. The heat is moving in this direction. Please, if you have a chance, go back to the differential control volumes unit, and you're gonna see that if you have a bar of length L that is insulated on the sides, and that was our first example for the differential control volumes, is exactly the same as a plane wall. It doesn't look like one bar is a bar and a wall is a very different type of system. However, from the point of view of heat transfer, under these conditions I'm discussing here, or the conditions I discussed in for the bar in the unit of differential control volumes, the equation is the same. The heat transfer is the same. It's 1D. Okay. What we saw when we did that, this analysis, is that the equation that corresponded is this one. So homework for you, and it's a homework that will be tested on quiz 2, and is see that this is the equation that applies to a plane wall, right? And this is the equation that came from doing a control volume with a differential thickness in the direction of x, and this is the transient term. This is the conduction, and I see there's a typo here. I didn't see it before. There's a typo. We're missing a t. This is Laplacian of temperature. So I'm sorry about that. And this is the heat generation term. You know how to derive this equation. If you don't know it right now, you'll know it in 2 weeks for the quiz. So in this equation, we need, we are saying steady state, that is the point in of this week. So if it is steady state, this term, is going to go away. Let's say for now, no heat generation. If you look at the book, they get also excited about heat generation. It's just math. But right now, to start, let's say heat generation goes away. I also, I put it in writing here, but I forgot to highlight the fact that we have this Laplacian. That means we're assuming constant thermal properties. Is it exact? No. Is it nearly exact? Yes, very, very often. Okay, so if this goes away, now the heat would depend only on X, Y, and Z, but not on temperature, not on time. If I have no heat generation, all I have is the Laplacian. It's missing T. Laplacian equals to 0. But there's more, because in the X direction, I have a gradient, but in the Y direction and the Z direction, that would be marking the plane of the wall. In the plane of the wall, if the wall has one wall at a constant temperature and the other wall at a constant temperature, that means the heat doesn't move sideways in the wall. That's why this is 1D heat transfer. So the derivative with Y is 0, and the derivative with Z is 0. You see, from all this equation, what we're left is with this part here. And isn't it beautiful? This is what I like. I got second derivative equals to 0. By the way, we saw this exact same equation when we did the first example in the differential control volumes class. All right. So we have this equation is, let's see, this equation is second order, is because it depends on only one variable, is an ordinary differential equation. It is linear and is homogeneous. Wow. So everything we ever might want in an equation, we got it. This is awesome. So the independent variable is X. There's no time because it's steady state. There's no Y and no Z because Y and Z are the coordinates inside the plane of the wall. And we say the heat transfer goes across the wall, but not in sideways in the wall. And because it's second order, we need two boundary conditions. So, and those typically you choose temperature on one side of the wall and temperature on the other side of the wall, two boundary conditions. Here we go. Temperature in 0, TS1, meaning T of the surface on the side 1 of the wall. Temperature at X equals L is TS2. I'm going to integrate this twice. I'm not going to spend much time on this, but you can follow it. It's integrating twice a second derivative. It's essentially trivial, and gives us the equation of a line. After we put in the boundary conditions, this is the equation of the line. Then we get to see at X equals 0, for example, this term goes away, and we have TS1. At X equals L, this X over L is 1. So we have TS2, and this TS1 here cancels with this one here. So we see it matches the boundary conditions. It's and tells us something we have speculated before, but we are proving it rigorously, that the gradient inside the wall, when the thermal conductivity is constant, is a straight line. Okay, let's calculate a heat flux in this case. In heat flux, we have is only in the direction of X, and by conduction we know that the heat flux is using Fourier's law. It's minus k dt dx. Here we have what I did here is I took out the minus sign and I flipped TS2 and TS1. Right, so we end up with like a better looking number. So the heat transfer is the heat flux is positive, and here TS1, the way we made the drawing, is bigger than TS2. if I want to look at the total amount of heat, the heat rate, Q, not Q double prime, Q in the direction of X, that is the amount of heat that is going through the wall, we would have area times this. And look at this. This is heat rate. This is temperature difference between the two walls. And here we have Ka over L, right? For a given wall made of a given material, say brick, with a given thermal conductivity, a wall has a given thickness, has a given area. This is a wall. This describes the wall, these three group in front. And what we see is what we mentioned before, just waving hands. We see that the heat rate is proportional to the temperature difference. This doesn't look like a big deal, but it's a huge deal, huge, because now we can say something that is amazing, and is, I can bank on the analogy between heat, in which temperature and heat rate is proportional to heat rate, or heat rate is proportional to the delta temperature, and electricity, in which current is proportional to the difference in voltage. And in electricity, we have Ohm's law that says voltage is proportional to current, and the constant of proportionality R is resistance. And in electricity, it has units of ohms. I'm going to say the same, and I'm going to steal the R symbol now for thermal resistance. So if you see R in this course, I'm talking about thermal resistance and not electrical resistance. When you use both, it's a pain, because you have to make two different R's. But we have no problem. R is thermal resistance, and delta T is thermal resistance times heat rate. The units of thermal resistance is not ohms, is Kelvin per watt. This K should have been a big one. I'm discovering all kind of little typos. So the thermal resistance, by definition, thermal resistance is defined as delta temperature over heat flux. And I didn't say it here, I said it before, but this is always positive. There is no negative thermal resistance. Delta temperature over Q, you get the sign convention right. Why to do this? Why? Not only you're learning heat transfer, but I'm asking you to remember differential equations. And now I'm asking you to remember circuits. This class doesn't get any worse, right? Okay, but this is a story. It is in an electrical circuit. This circuit here, where we have three resistors in series, is a trivial problem. Trivial. Now, in heat transfer, the equivalent of this is a very complex system. But if I turn my walls and my other resistances we're going to see into electrical resistances, I turn it into this, and I laugh all the way to the bank. But if you don't use the concept of thermal resistance, like, for example, physicists, they think they know heat transfer, right? They start Schrödinger's equation and they can calculate everything. Yeah, except that they would need hundreds of years to calculate what it takes you a few minutes, because you are using all these engineering formalisms that helps you like think of very difficult problems using tools that are very powerful and also enhance your intuition. So to give you an idea, back to our friend, the heat exchangers, this is the circuit that is typical of a heat exchanger. Actually, a heat exchanger has more resistors than this. And if you say, okay, but what about a heat exchanger with fouling? I would say, haha, no problem. I have a resistance here. You say, no, I have fouling inside and outside my tubes. Okay, another resistance. We can't lose. This is awesome. But in addition to this, we can say, okay, how about parallel resistors, like this one here? For example, this is the case of a surface that loses heat by convection, and at the same time, the surface loses heat by radiation, right? This is so cool. To give you an idea, this last week, I had a consulting case in which they paid me okay, and I'm very happy with it. And the whole problem for a big company, the whole problem was solved using this one parallel resistance circuit. Yeah, and the resistances, how they are calculated, you're going to see it later, because that was for a more advanced problem than steady state is transient, which we will also see. So there's a point to this. That's my point, is that there is a point. Okay, so I want to mention a concept associated with thermal resistance, and it's a concept that has a horrible notation, and acknowledging that it's horrible, I have not come up with anything better. So I'm gonna use the same the book uses. And it's the concept of resistance per unit area. So we saw that resistance is delta T over Q. This nobody takes away. But if instead of Q, instead of heat rate, I use heat flux, Q double prime, right? Delta T over Q double prime, I get a resistance I'm gonna call R double prime. Now, Q double prime is heat rate, Q, divided by area. Typically, the double prime means per unit area. However, and this is the terrible thing that confuses everybody, including me, but it's the way it is, and I have not found a way to do it better, and by the way, nobody has found, is, you see this R double prime? This R double prime is resistance times area, not resistance divided by area, it's times area. And you can see why, because the Q double prime, when it goes at the bottom, the area that was dividing the Q goes on top. Most unfortunate, because R double prime, it can be so confusing, but it's such a useful concept that we will be using it a lot. And I wanted to bring it in the clear, acknowledge the horror of the notation, and then move on and use it, right? And so I have a minute here. Let's look at the thermal resistance of a plane wall. So we have TS1 on one side, TS2 on the other side. The heat is flowing across the wall. That's the point. The heat is flowing across the wall, and it's not flowing up or down or in or out the screen. The thickness of the wall is L. What is the analog of this real life case, this real life problem? The analog is this. We have a resistor that that represents the wall. TS1 is one end of the resistor, that means this surface. TS2 is the other end of the resistor and represents the other surface. So this is the wall and the resistance of the wall. And you see two batteries here. This battery is this, the batteries are voltage and are the analog of temperature. This battery is TS1. The voltage here is TS1. This other battery here has a voltage TS2. See, TS2, TS1. And they go to the ground. Ground is 0, right? Ground is 0. So what is the resistance of this plane wall? Okay, we have heat by conduction, which we know because we did in week 2 of class, is Ka over L times delta T. week 2 of class. And we did it again today from the differential equation that we saw in week 4 of class for the differential control volumes. We ended up at the same place. First, we did it intuitively. Second time, we did it formally. But we end up here. So the definition of resistance of conduction is delta T over Q. I apply this definition, and I have delta T. I pass this Q dividing, and this L and Ka, I pass it to the left. What do I get? The resistance from applying the definition and our knowledge of how to calculate the heat transfer by conduction is L over Ka. And if we do R double prime, that is resistance times area, is L over K. Think of this. For R, the conduction is the thicker the wall, the more resistance. Duh, right? But it makes sense. I'm happy it makes sense. The higher the thermal conductivity, the less resistance. The bigger the wall, the more resistance. And same per unit area. So L, thickness, thicker jackets, more thermal resistance, better for the winter. There you go. Better insulation, lower K means higher thermal resistance too. Right? We already understand jackets now just by looking at this, but much better than this. We'll be able to calculate the jackets in a windy day, whether there is sun shining on it or not, and how big you are. Let's stop here, and I'll see those of you. I'll hold office hours at 2. Look forward to seeing you there. Thank you.